Welcome to an introduction to relative extrema for multivariable calculus. Let's take a look at a couple of surfaces here. On our surface on the left, we see what appear to be two relative maximums, or local maximums you might refer to them. And so we might wonder what's the criteria for a point like this to be a local maximum. Well, the criteria is that there has to be a point x0, y0 in the xy plane, so a point down here, such that this is the output up here. And if I come down to this point in the xy plane, that the function value at this point is greater than any other function value in an open disk around that point. So if, for example, this output value was generated by this point here in the xy plane, then if I pick any point in an open disk around that point and evaluate my function in any point, at any point in this disk, that function value from that point will be less than the function value at the x0, y0 that produces what we think the maximum is. Same is true here for a minimum. It looks like we have a relative minimum or a local minimum here, and it looks like it's probably at the origin. So let's assume that we think that that's our the xy value that produces our local minimum. So then that is a local minimum if we can take and create a disk around that xy value that produces what we think is the minimum. And if I choose any point in this open disk, the function values, the output for the function for these points, is always bigger than or greater than the function value at this point x0, y0. So let's recall a little bit of what we know from single variable calculus. So in single variable calculus, a typical problem would be something like find the relative extrema of the function f of x equals x cubed minus 6x squared. So the critical steps, the crucial steps in finding that those relative extrema using calculus is first we had to find the first derivative. So in this particular case, that first derivative would be 3x squared minus 12x. Second, we had to find critical points for f prime of x. So there were two components for finding the critical points for f prime of x. The first was to solve for where our derivative was equal to 0. In this case, that would mean we were interested in the points x such that 3x squared minus 12x is equal to 0. The second source of critical points was locations where the derivative does not exist. For this simple example we have here, that means we'd be asking ourselves, where does 3x squared minus 12x not exist? So let's answer those two questions. So if we're interested in where our derivative equals 0, in this particular case, we would factor and get 3x times the quantity x minus 4, which gives us two critical points, x equals 0 and x equals 4. If we're considering where does 3x squared minus 12x not exist, well, the answer to that is nowhere. Our derivative function is defined for all real numbers. So we really only have two critical numbers, x equals 0 and x equals 4. Once we had our critical points, then we used either the first derivative or the second derivative test to detect the presence of extrema. So just because we had two critical points does not mean we have two extrema. So In the case where your function is a polynomial and the second derivative is easily found, I typically use the second derivative test to perform this test. So in this example, our second derivative, or the derivative of the first derivative, 3x squared minus 12x, that second derivative is 6x minus 12. We evaluate at our two critical points, so f prime at 0 is 6 times 0 minus 12, and f double prime at 4 is 6 times 4 minus 12. And with the second derivative test, we aren't necessarily interested in the numerical value of these two second derivatives. We're particularly interested in whether that second derivative is positive or negative. So when I look at 6 times 0 minus 12, I've got 0 minus 12. I've got a negative number, so this is less than 0. If that is less than 0, then that means that we have a relative maximum. At x equals 0. And then if I evaluate my second derivative at 4, I have 6 times 4 minus 12. 6 times 4 is bigger than 12. So this is going to be a positive value. And so this will be a relative minimum at x equals 4. So while I might have been able to graph this function and determine whether they were relative maximums or minimums at these critical points, we do need to know how to use calculus to do so. So now let's establish the definition of critical point in a multivariable setting. So if z is a function of two variables, let's say x and y, and it's defined on an open set that contains that point x naught, y naught, where we think we have a max or min, the point x naught, y naught is a critical point of the function f if one of the two conditions holds. And notice that these are similar to what we did in single variable calculus. So we have a critical point if the partial derivative with respect to x at that point is equal to the partial derivative with respect to y at that point, and basically they both have to equal 0. If both first partial derivatives equal 0 at a particular point, then we have a critical point. Alternatively, we could have either the first partial derivative with respect to x at the point not exist, or we could have the partial derivative with respect to y at that point not exist. So these are very similar to what we did back in single variable calculus. So let's look at a simple example of finding critical points. So we have a function here, f of x and y. It's equal to x cubed plus 3y squared plus 6xy minus 18x minus 9y plus 4. Recall that for us to detect the location of a critical point, we need both first partial derivatives. So let's go ahead and find those partial derivatives. So when we're finding the partial derivative with respect to x, we treat the variable y as if it were a constant. So the partial derivative of our first term with respect to x is 3x squared. The partial derivative of our second term is 0, so I'm not going to write that. Of my third term, the 6 and the y I treat as constants. So I have 6y, and then the partial derivative of x is 1. So this would be 6y times 1. Then our next term is minus 18x, so the partial derivative with respect to x there is minus 18. Moving on, these last two terms, partial derivative with respect to x, will be 0 for both of them. Now, the partial derivative of f with respect to y, this first term, that partial derivative will be 0. Our second term will be 6y. Our third term partial derivative with respect to y, we treat the 6x like it's a constant, and then I take my partial derivative with respect to y, and that's 1. The next term is the partial derivative is 0 with respect to y. This next to last term, that partial derivative is minus 9 as my constant coefficient, and the partial derivative of y with respect to y is 1. And then lastly, the partial derivative of 4 with respect to y is 0. So now that we have our partial derivatives, now we want to consider where those first partial derivatives both equal 0. So we're looking for a point that causes them both to be 0. Alternatively, we could be looking for a point where our first partial derivatives do not exist. However, these partial derivatives are polynomials. They're nice and continuous and defined everywhere. So this is not an option for critical points. So we're going to focus our efforts on finding points where f of x equals f of y equals 0. So this ends up creating a system of equations. So I've taken my partial of f with respect to x and set it equal to 0. I've taken my partial of f with respect to y and set it to 0 as well. Notice that I use the commutative property of addition to rearrange the x term and the y term so that like variables were in the same position. So notice then I have this system of two equations, and we have two unknowns, our x and our y. So what I'm going to do is I'm going to subtract these two equations. So I'm going to subtract the second equation from the first equation. Now, when I do that, I can distribute that subtraction and turn it into addition. So this becomes a negative 6x, this becomes a negative 6y, and this becomes a positive 9, just making it easier to keep track of our signs. So adding down in columns, if you will, I've got 3x squared. There's no x squared in the second equation, plus, and then I've got this negative 6x, so I'm going to write that as negative 6x. So that's adding within this first column. Now, in the second column, notice that our 6y terms, they will sum to 0. So I have no more y terms left in my equation. Then I've got negative 18 plus 9, that's going to end up being a minus 9, equals 0. And now I have a little quadratic equation to solve. I notice I have a common factor of 3, so I'm going to start by factoring out that 3. After factoring out the 3, I've got a nice little trinomial to solve. So I can factor this to be 3 times x minus 3 times x plus 1 equals 0. And then I find that with x coordinates equal to negative 1 or 3, I have both of my partial derivatives equal to 0. At this point, I just need to figure out what the corresponding y values are for these critical points. So we're going to take our first critical point, x equals negative 1, and we're going to substitute it into one of these two equations. I'm choosing the second equation to avoid the need to square any numbers. Also notice that while I can substitute for x, I am going to have to solve for y. So this is going to end up giving me 6 times negative 1 plus 6y minus 9 equals 0. So I have a negative 6 and a negative 9. So that's going to be a negative 15. So 6y equals negative 15. I'm sorry, 6y plus a negative 15 equals 0. Let's go ahead and add 15 to both sides of that equation and then divide by 6. So I end up with y equals 15 over 6, which simplifies to be 5/2. So now I have a critical point that is -1, 5/2. We repeat the process with x equals 3, and we have 6 times 3 plus 6y minus 9 equals 0. 6 times 3 is 18, and 18 minus 9 is 9. So we have 6y plus 9, because 18 minus 9 is 9, equals 0. And then let's go ahead and subtract 9 over to the right-hand side and then divide by 6. So y equals -3/2. So our critical point here is 3, -3/2. So we have 2 critical points for this particular function. I hope you find this helpful.